In this video, we're going to take a look at the graphs of the original trigonometric functions. So that includes sine, cosine, tangent, cotangent, and then we'll look at cosecant and secant as well. We'll take a look at how those graphs impact our decision for how we're going to restrict the inverse functions. So let me go ahead and show you here. Let's just take a look at the sine function. So let's say we have y is equal to sine of x. Okay, and we'll graph that guy out. So hopefully you've got the graph of it memorized. So we'll re-sketch it out here. So we know that the sine function starts at 0, moves up, and comes back down like this. And of course, it repeats itself, so it looks something like this. That's our sine curve. Now the problem is, in order for an inverse to exist, so if we want a function to have an inverse, the original function must be 1-to-1. Now, if you don't know what 1-to-1 means, okay, then you need to go look that up, because that's something that's covered in a typical college algebra class. Okay, but the test for something to be 1-to-1 is for it to pass a horizontal line test. So notice that if I were to draw a horizontal line, let's say here, the sine function fails the horizontal line test because it would cross at 2 spots. Okay? So what we have to do is we have to restrict the domain of this function right here so that it passes a horizontal line test. So what we do is we section off the graph from here to here. So this area is all we're looking at. So we'll take away the rest of the curve like that. And this right here is what we're going to look at. Okay? Now this has an inverse because this passes the horizontal line test. So if you notice, we went from negative pi over 2 to pi over 2. So what we said was if we restrict sine to have inputs on the interval or between negative pi over 2 and pi over 2, then this guy right here exists. Now we have an inverse trig function. Notice that if we tried to go from 0 to pi, if I tried to go from here to here, it wouldn't exist because I would not pass the horizontal line test. So that's why we restrict it to this. So what this tells me is that if we restrict sine's domain, this is the domain of the restricted sine function, then the range of the inverse sine is also equal to that guy. Because when you deal with inverse functions, the domain becomes the range of the inverse, and the range of the original function becomes the domain of the inverse. So think about that. The original sine curve, its domain, well, it's restricted. Let's write it like this. So for the restricted sine function, its domain would be from negative pi over 2 to pi over 2. Its range, the values that we can get out, are from negative 1 to positive 1. Well, for the inverse, the domain and the range swap spots. So this guy goes here, this guy comes down here. Let's draw that a little bit better. So the domain of the arc sine is from negative 1 to 1, and the range of the arc sine is from negative pi over 2 to pi over 2, just like that. So what we're doing is we're using the original curve to set up our inverse. Now the same thing applies with cosine. So let's take a look at cosine. So let's say y is equal to cosine x. Well, let's graph that guy out. So here is negative pi over 2, negative pi over 2 and pi, 3 pi over 2, 2 pi. Of course, we go from 1 down to negative 1. Cosine starts at a height of 1, then drops down, comes back up. So it's going to look something like this. This is our cosine curve. Now again, the problem is for it to have an inverse, to have an arc cosine, for the inverse cosine to exist, cosine of x has to pass the horizontal line test. But it doesn't, right? Clearly, it doesn't pass it here, it doesn't pass it here. I mean, there's a whole bunch of spots where it doesn't pass it. So what we need to do is we need to restrict the domain of the cosine curve for it to get an inverse. Now, we can't restrict it from negative pi over 2 to pi over 2, because if we use this interval, we don't pass the horizontal line test. So we can't use the same interval, the same domain restrictions that we did for sine. Doesn't work here. So what we do is we pick new ones. And so the new ones that we're going to pick are from 0 to pi. Now, if we delete everything else, notice that that guy from 0 to pi passes the horizontal line test. So what we're going to do, we've got a domain and a range. The original cosine function, its domain, well, we have to restrict it. If we don't restrict the original, then we don't get an inverse. So we're restricting the original to have a domain from 0 to pi. We're only going to look at this interval right here. Now, of course, its range is the y values that we range over, that we can get out, are from 1 to -1. So we'll go -1 to 1. We have to write it in the correct order there. So, again, when we're dealing with inverses, we switch the domain and the range. So the arc cosine has a domain value. We can plug in any number between -1 and 1 inclusive, and our output is going to be between 0 and pi, just like that. So for example, this is okay. If I say what's the arc cosine of, let's say, 1/2, well, 1/2 is between -1 and 1. So the guys that get plugged in here, the domain, the guys that are plugged in, okay, this guy is between -1 and 1, so we're good. The output has to be between 0 and pi. So we're looking for an angle that has a cosine value of 1/2, and we know that that's pi over 3, and pi over 3 is clearly between 0 and pi. Now tangent's a little bit different, so let's do tangent here. In purple, and here's why tangent's different. Tangents, well, let me graph it out for you first, and then I'll explain why. Okay, so the tangent function. So we're gonna go with y is equal to tangent of x. Well, we know that tangent has vertical asymptotes, and I'm going to do those in red here. Has vertical asymptotes whenever it's undefined. And we know tangent's undefined at 90 degrees. Tangent's undefined at 270 degrees. And of course, it would be undefined at -90 degrees as well. We also know that tangent starts at 0 and then increases, so it'll look like this, and it would come down like this. Of course, this side looks like this, and you should know what this curve looks like and have it memorized. Notice that it repeats itself. To repeat this guy, we had to go every pi. So the period of tangent is pi, and we've discussed that. Now, what about the inverse? Well, notice that the entire tangent function, since it repeats itself, doesn't pass the horizontal line test. Look, we fail here, here, and here. So we need to pick a restriction. Now what we're going to do is we'd like to have this so that the function's continuous. Now we can pick whatever we want. For example, I could pick 0 to pi. Because if I went on the interval from 0 to pi, I have this piece up here, and I have this piece down here, okay? And I would pass the horizontal line test as long as I didn't include either 0 or pi. Okay? But the problem is that the function is discontinuous on that interval. So, just for convenience, for no other reason besides convenience, is that we're going to pick the interval from here to here. Now, what that allows us to do, of course, we can't include the endpoints because tangent's not defined at those endpoints. But it does give us a nice continuous function. And so, for some reasons, I mean, it's very nice for calculus to have continuous functions to work with. So we're going to just use this interval, and we're going to ignore tangent everywhere else. So this is going to be what we're going to restrict our tangent domain to. Now this is only when we're dealing with inverses, of course. If we're dealing with just the original tangent function, in any other situation, all bets are off, and we're going to use the whole curve. But just dealing with the inverses, okay, we're going to look at this restriction. So what we're going to say is for arctangent to exist, the original tangent function domain has to be restricted. And we're going to restrict it from negative pi over 2 to pi over 2. Notice I use parentheses here because tangent's not even defined at negative pi over 2 or pi over 2. Give me 1 second here. Now the range value, well, the range of this line, well, it takes out every single value, anything you want for y. So the range is from negative infinity to infinity. So by doing this restriction to the tangent function, we create an arctangent function, the inverse tangent, whose domain is negative infinity to infinity, which means that if we take arctangent, we can plug in whatever we want. Any real number can go in here. And what will it output? It'll output values between negative pi over 2 to pi over 2 exclusive, so not including those. So there's our domain and our range for our inverse tangent function. So it tells us what we can plug in and what we can see come out. Plug in any number we want to here, and the only guys that we can see out are on this interval. Now for cotangent, let's draw a cotangent's graph out here. And so for cotangent, again, cotangent has, well, let's plot this out. So negative pi over 2. We'll do this guy in orange. So looking at the original cotangent function, we don't draw this one out that much, so it might not be as familiar to most math majors. But let's go ahead and see if we can reason through why the curve looks the way it does. Well, the first thing is that we've got vertical asymptotes, and we've got to figure out where those guys are at. So cotangent, if you remember, is cosine over sine. So whenever sine is 0, we've got a vertical asymptote. So that'll happen here at 0 radians. It'll happen again at pi, again at 2 pi, and negative pi. Now, it is 0 whenever cosine is 0. So that'll happen here, here, and here. Now we have to talk about the direction that it's headed. So, as we head towards pi, in this interval right here, between pi over 2 and pi, if you think about a unit circle, all students take classes piece is nice here. Between pi over 2 and pi, sine is negative, but cosine's positive. So the overall result is negative. Over here, between 0 and pi over 2, both of them are positive. So we're both up in the air. Okay? And of course it repeats itself very nicely. So it looks like this. Now, this is the cotangent function, but again, it fails the horizontal line test horribly. So what we're going to do is we're going to restrict it, and we'd like to restrict it. We could restrict it to the same thing that tangent had. Okay? Same restriction. However, if we restrict it between negative pi over 2, Let's get that guy out there. And pi over 2, if we just use these pieces, then we have a discontinuous function. So it would be nice to have continuous, so for convenience, we're only going to look from here to here, and we're not going to look at anything else. Okay, so this is the restriction on cotangents so that it has an inverse. So we'll say cotangent of x and cotangent's inverse, like that. So the domain for cotangent is being restricted, not including 0, we can't include it because it's not even defined, and not including pi, but that's our interval. And its range is anything we want. We get any hideout we want. Think about range as if you're standing on the x or the y-axis looking left and right. Where would you see a curve? Everywhere. Well, again, these rotate. They change spots. And that gives us our domain and our range for cotangents. So, for the inverse, excuse me. So, for the inverse, you can plug in any number. The only guys you can get out are between 0 and pi, not including them. Okay? If you give me a number out here that's different than this, no points, because you have to follow what the range is. Now what about secant? Well, there's really, when we work with secant and cosecant, so let's talk about the picture here, the graph for secant. So secant is the reciprocal of cosine. So secant, whenever cosine is 0, secant's not defined. And we know cosine is 0 at pi over 2, at negative pi over 2, at 3 pi over 2, so on and so forth. Now, we also know some information about the height values. We know that cosine at 0 is 1, which means secant is 1 over 1, which is 1. Now here's the thing. From 0 to pi over 2, the cosine values get smaller and smaller and smaller. So we're taking 1 and dividing it by a proper fraction, which means all these numbers are going to be greater than 1, and they're going to increase. So it's going to look just like this. Same thing with the other side. If you don't believe me, my advice is take a value like pi over 4 and plug it into this guy right here. Take 1 divided by the cosine at pi over 4, and I bet you get a number out that's higher than 1. It's going to be somewhere right up here. Now when cosine is pi over 2 and negative pi over 2, it's undefined, so secant's undefined. At pi, cosine is negative 1, so we have 1 over negative 1, which is down here. And for the same reasoning, we get the curve to look like this. And it's going to repeat itself because cosine repeats itself every pi over 2. Excuse me, every 2 pi. So is secant. Now the question really is, where do we define our domain for secant so that we get an inverse? Because notice we failed the horizontal line test. Well, the problem the problem that's really involved here is I can't use any of these loops because all of these loops will fail. So I got to pick a half of a loop on one and then a half a loop on the other. Well, where do we pick those half loops? So this isn't easy. Well, I shouldn't say it's not easy, but it really has to do with how you want to define it. And now different books will define it different ways, and in your calculus class you may define it differently. So in this class, to make it easy for us to remember, since secant is related to cosine, we're going to use the same restrictions that we did for cosine. So we're going to restrict the domain of the secant function to be between 0, I'm going to draw this out for you because I'm going to have to union it, from 0 to pi. So all that we're using is these two pieces, this piece and this piece. But notice that they're not defined at pi over 2. So we're going to go from 0 to pi over 2. We're not going to include it. And we're going to union that with pi over 2 to pi. And we can include pi. So what we've done is we've used this and this because it passes the horizontal line test, but we can't use pi over 2, so that's why we restricted it here. Okay. Now the range, the outputs are from -infinity to -1. We never include infinities because they're not numbers. And then we're going to union that with 1 to infinity. So what this tells us then is that this guy, for the arc secant, this is the domain for the arc secant. I don't have enough room to write it over here. And this guy up here, this is the range for the arc secant. So if we put arc secant here, the guys that we can plug in are from -infinity to -1 or 1 to infinity, but we can't plug in any numbers that are from -1 to 1 exclusive. So like if I try to plug in 1/2, well, that's a no-go. The function breaks down, okay, because it's not in the domain. And in fact, the other way to think about this is we're looking for an angle whose secant is 1/2. Well, that's impossible. Secant doesn't have a value of 1/2 out. Okay, you can't get 1/2 out here. There's no function anywhere in between here and here. So it's impossible. Now, the only values that we can see out for the range, the only angles that we'll look at are from 0 to pi, excluding pi over 2. Now, the same thing, the same story, I won't go through the whole thing, but the same story is used for cosecant. So for cosecant, we would have to pick what we wanted our range to be over in order to, our domain to be restricted to in order for this to have an inverse. So for cosecant, we'll follow sine. So what we'll say is for cosecant of x, its domain, sorry, it gets tough to write over here on the side. Its domain will be the same as sine from -pi over 2 to pi over 2. But here's the deal with this. Cosecant is not defined at 0 because sine is 0 at 0. So we'd have 1 over 0, and that's not defined. So what we need to do is split this thing up. So we're going to go from -pi over 2 to 0, not include it, and then from 0 to pi over 2. This is just a fancy way of saying go from negative pi over 2 to pi over 2, but don't use 0. Of course, the range of this is the same as the range up here that we had because we get the same type of graph that spits out. So from negative infinity to negative 1, union from 1 to infinity like that. So that means that the arc cosecant or cosecant's inverse, its domain is this guy, and its range is this guy.